Today we're going to talk about solving linear systems. You've done this stuff before. Okay, so you've done this before, but I want to do more than just knowing how to solve linear systems. We'll talk about ways to solve linear systems. But before we jump into that, we even want to talk about, what do we mean by solving a linear system? What's it mean to solve anything? So like if we're going to solve this equation right here, this blue equation, look at that for 5 seconds. And I bet you can tell me the solution. What is, I'm seeing 4, right? Everybody says 4. Okay, good. Well, that's correct. The solution is 4. How come? Okay, but I want to know why is the solution 4, not how'd you get it. Say it again. Yeah, because 2 times 4 minus 1 equals 7. Because if I plug 4 back in for x, it makes the equation true. In math, we'd say it satisfies the equation, right? X equals 4. So it is the solution. Yeah. Okay, so that was a piece of cake. No big deal. Solve this one. Like, tell me the x value that works. Okay, I'm getting some blank stares. How come? What's different about this one? There's x's and y's. Okay, so this is different. So we can't just solve this and get a single answer for x, right? If I solve this for x, I'm going to get, well, I'll pick a value of x that works, 10. Okay, 10 works, but just saying x equals 10 isn't enough. I could say something like, is 10 a good one? It's not so great. Why don't I pick something different? Why don't I pick something like 2. So what if I pick like x equals 3? That would work. That's an easier one. I mean, any of those would work, but if I pick x equals 3, that is a solution, but what's the value of y that would have to go with that value of x?
2. Wait, -2. Yeah, -2.
Negative 2?
Yeah.
Okay. Yeah, that works, doesn't it? Okay. But that's not the only one. I could pick, for example, how about if I pick 6?
0.
Okay. What if I pick 9? 2. Okay, we could play this game all day. How many solutions are there? How many ordered pairs are there that would satisfy that original equation? An infinite number, right? So you see, this is a different kind of thing. If I've got an equation with 2 variables in it, I can't come up with a single solution. What we're going to find is I'm going to need to have at least as many equations in a system as I have types of variables to come up with a single solution, right? I've got 2 kinds of variables here, x's and y's. So in order to pin down a single solution, a unique solution, we'd say in math, I would have to have how many equations in my system? 2. I need 2 linear equations to come up with a single solution. Okay, let's explore what just happened here though, right? If we've got this equation 2x minus 3y equals 12, there it is. There is that equation. Okay, let's make it big. 2x minus 3y equals 12. Well, if I drag my cursor, if if I drag a point along this line in Desmos, look, it's giving me an unending stream of ordered pairs. Those are all decimal numbers that I could plug in for x and y that would satisfy the equation. There are an infinite number of those, right? Okay, well, let's look at a system. There's another equation. Okay, how many solutions are there to the green equation? I mean, how many ordered pairs would satisfy the green equation? An infinite number, right? And I can see that here. Look, if I turn the red one off and turn the green one on, there are an infinite number of ordered pairs that would satisfy the green equation. We could come up with some if we wanted to, right? Okay, but if I want to solve this system, what am I looking for? If I want to solve this system of two equations, what am I trying to find? Okay, x is part of it. I want to find an x value and a y value. But if I'm solving something, I have to find, like I solved for a value of x here that satisfied the equation. When I plugged it in, it made it true. If I'm trying to solve a system, I have to find values of x and y that do what? Okay, that make the red equation true and the green equation true. Okay, well, let's look at that graph. So how many points are there that do that? One. Where is it? It's at the point of intersection. There you go. Okay. So there's only one point that sits on both those lines at the same time, and that's the point of intersection, right? Okay, you get the idea here? So when we're trying to solve a system of two equations and two unknowns, we're trying to find the point of intersection of the graphs of those two equations. If I were going to graph them, I don't have to, but if I did, the solution is the intersection, right? Well, we're going to go beyond that. We're going to stretch your brains a little bit in this section, and we're not just going to limit ourselves to simple 2x2 linear systems. We might look at things like 3x3 linear systems. Now, those are things that we could think of in terms of a graph. It's just a more complex graph. Now, instead of the graph being graphing lines on a plane, we're going to graph something in a space because we need 3 dimensions. So I'm going to have an x-axis, a y-axis, and a z-axis poking out of the board, right? Ooh, so now we're trying to find some different kind of intersection. What if we solved a 4x4 system? How would you graph that? You can't, because it's impossible to do in our universe. We only have 3 orthogonal dimensions in our universe, so we can't graph a 4-dimensional linear equation. We just couldn't do it. But we can still find solutions to a 4x4 linear system using the same techniques that we used for a 2x2 linear system, right? So we could extend all the way up to much, much higher dimensions if we want to. Okay, but we'll get there when we get there. So let's just talk about systems of equations. So filling in our notes here. Systems of equations, that's all that means. We talk about a system of anything, in this case equations. It's just more, or I'm going to say more, I'll just say multiple, I'll just say more than one. More than one equation taken together. That's the definition of a system of equations. Okay. If it's a system of linear equations, then it's more than one linear equation taken together. And that's what we'll start with. They're just systems of linear equations. Well, how could we get a system of linear equations that has one solution? Well, we just looked at that, didn't we? Right? If we have a blue line and a red line, I get a single solution if the lines intersect. And there's my one solution, right? Okay, how could I get a system of linear equations, I'm looking at the graphs now, where I have no solutions? Parallel. Okay, if they're parallel. Yeah, they never cross. Okay, so I could do something like that. How could I have an infinite number of solutions? Oh, if the lines overlap completely. Okay, so I have something like this. Okay. All right, well, let's practice finding these. There are different ways to go about solving systems. One way to solve systems is using technology. Okay, so let's practice that. On Desmos, it is so simple. So on Desmos, if I want to graph, if I want to find the solution of this system, what do you think I do? I just enter both lines in and find out where they intersect, right? Just graph them both. So y, and if you guys want to bust out your Chromebooks and open up Desmos graphing, go ahead. Just work along with me here. So y equals negative 5/3 x minus 6, and y equals 1/6 x plus 5. Okay, now I can't see the intersection, so what do? I just have to drag the XY plane, or I could zoom out if I want to. I just have to be able to see the intersection, and then I just graph on that point, and there it is. There's my solution. X equals -6, y equals 4. Okay, easy. How do I do this on my TI-84? So bust out your TI-84s. I'll show you. On the TI-84s, I do the same thing. I just go into y equals and I graph both lines, making sure all the plots are turned off. So y1 equals -5/3. Okay, so how do I deal with the fraction? A couple ways. If I don't want to mess around with a fraction template, I can always just put fractions in parentheses and treat them like a single number, right? Something. So I could just put in parentheses -5/3, close the parentheses. There it is. There's my fraction times x minus 6. Okay. If I want to, I can use the fraction template. The fraction template. If you have a TI-84 plus CE, one of the new ones, they conveniently put it right behind the variable button. If I just hit alpha x, it gives me the fraction template. That's kind of nice. Okay, if you don't have one of these, how do you find it? Well, there's a couple ways. You could do alpha F1 and go to the fraction menu and just choose the first option. Or you could go to the math screen and scoot over to the number menu and just go all the way up to the very bottom. So just like if you go up, it'll take you to the bottom of the list and you'll keep working up and choose that option. Whichever way you choose, there's my fraction template. So 1/6 x plus 5. Okay, now how do I graph this thing? What do I do? Do I just push graph? No, what should I do instead? Zoom 6. Yeah, zoom standard. So we go zoom 6 and see if that works. If it doesn't, we might have to zoom out a little bit. Okay, but it does work. We can see the intersection. And that's the thing on the graphing calculators. In order to find this intersection, you have to be able to see the intersection on the screen. Okay, so now what? Well, anytime I want to do something with a graph, remember what you do. You go second calc to get the calculate menu. And which of those options do I want here? Number 5. I want intersect. So second calc 5. And now I just have to tell it which are the two lines that I'm intersecting. I only have two. Is the blue y1 the first curve? Yes, so I hit enter. Is the red y2 the second one? Yes, so I hit enter. For my guess, I'm just going to trace over reasonably close to the intersection and hit enter. And there it is, -6/4. Okay, so I'll just put that on here for our notes. So let's try another one. Okay, try this one. Now this one is super easy on Desmos, right? All I have to do in Desmos is literally just type those in just the way they're written. So I'm going to erase these. Okay, what's really nice about that is I don't have to solve for y. I can just type in 6x minus 5y equals negative 45. There's the line. 2x plus 2y equals negative 4. There's the line. And there's the intersection. So that's my solution, right? Very simple. Okay, it's a little tougher on the TI-84 to do this one. So I want to show you a trick. So if we go to the TI-84, go to y equals, and let's clear both of those lines. Okay, what do you notice that's inconvenient about the TI-84 for this system? Yeah, you got to isolate the y. Has to be solved for y. Okay, so there's a way to do this, though, pretty easily. I just call this solving into the calculator. So we're going to do the algebra steps in our mind right into the calculator. In the top equation, so that'll be our blue one, right? That top one. Let me keep this thing on top here. There we go. Always in front. Okay. So first line is blue. So for the blue line, what are the two algebra steps to get the y by itself? What do I have to do first? Subtract 6x, right? To get rid of that. Then I divide everything by negative 5. So one way I could do this, being as I'm going to have to divide a bunch of stuff on the right side by negative 5, I could open up a set of parentheses, open up a quantity. And what's already on the right side? Well, a negative 45, right? You guys told me I'm going to subtract to the x side 6x. So I'm going to do negative 45 minus 6x. Then I'm going to close the quantity so I can divide the whole thing by what? Negative 5. Okay. And if I graph this thing, there it is. There's my line. Okay. So you graph it, you either just push, like I just pushed the graph button because I knew I had already done Zoom Standard last time. Yeah, go back to there. Okay, what do we got? Okay, I'll help you. I'm going to troubleshoot this because it's by making mistakes, you kind of learn how to solve these mistakes. So what did you get here? It says invalid dimensions. Yes, I know what you did. Okay, what's wrong with that? You got your plot on. Oh, I did two things. Okay, so this is something that drives me nuts about the TI-84. So does everybody see that? You can't see this, but you've probably had this experience. When you go into y equals and you have little, they look like, I don't know what that even looks like, a triangle pointing at a rectangle at the top. That means you're in the transform program, probably from last year, I bet, from pre-calculus. I bet. Did you use this thing in pre-calculus a little bit? Really? Not at all. No, you don't. But your plot is on. So if the plot is on, see, it'll look like this. I'll give this back to you, I promise. If the plot is on, it looks like that. The plot is highlighted, right? I want to turn that off. So if the plot is highlighted, you have to go up and unhighlight it. Okay, so that's one problem. That might be the only problem, actually. If I turn that off, come back down and hit graph. Yeah, now it does it. Okay, but you kind of want to get out of that program too. So the way you do that is you go apps, and I always do this. I always just go into like inequality, and then yeah, there it is. You quit right there. You quit apps listed below. So quit transform. Press any key to continue. And now I'm going to go apps, and I want to, how do I get out of that then? I think I go inequality, quit. There's probably an easier way to do it, but that's how I do it. And now notice you don't have that goofy thing over there on the side. Okay? Say it again? I don't even know what that program's for, honestly. I've never used it.
Because I have the plots off.
Okay, you hit go to, and what's it say? Oh, here's the problem. Look, that has to be a negative, not a minus. Minus is what you use, right? So it has to be that. Okay, there you go.
I just put in a random thing, and whenever I go
to graph. Okay, it's because your window's messed up.
Yeah.
Yeah, see, because look, your window is going. So what you can do is just hit zoom 6, and it'll reset the window.
Okay.
See, from negative 10 to 10, negative 10 to 10. Okay?
Yep.
Or you can just manually resize the window too. Anybody else having issues? Okay, all the trouble was up here. Wow. Okay. All right. So that's one way. One way to do it is to use parentheses. Now the other way would be, let's go ahead and use that fancy fraction template. So for y2, I'm going to go ahead and pull up my fraction template and solve for y in the red equation. We'll solve right into the calculator again. Okay, you have a question? Okay, so what are the steps to isolate the y in the red equation? Okay, I'm going to subtract 2x. I already have a negative 4 on that side, right? So on the top of the fraction in the numerator, I'm going to type a negative 4. It has to be a negative 4, not a minus 4, right? And you told me to subtract 2x to that side. And then to get the y by itself, I have to divide everything on both sides, including the right side, by 2. And now if I graph, there's my intersection. How about that? No, doesn't make any difference. Yeah, amazing. So I'll go second, calc, 5, and really all you have to do if they're lines is just triple enter, because I only have 2 equations that I've graphed. So I hit enter for y1, enter for y2, and do I even need a guess? No, they're lines. It'll find the intersection without getting close to it, okay? So you can just go, you can go second, calc, 5, triple enter, and there's your intersection. Okay, so moving on. How about try that one? Okay. Let's try this. And I'll tell you what, just to save time, let's go through this one together. So if we go y equals, clear. So the top one we have to solve into the calculator. So let's see, pick a brave soul here. Jake, tell me, what am I gonna do to graph the first one?
to graph it,
Yeah.
you do parentheses.
Okay, parentheses.
Would it be negative 3x minus 12
Okay, I'm just gonna start with what I already have there. Negative 12
minus 3x?
minus 3x. Because remember, you see, the point is, I don't have to simplify anything, right? I don't have to make it into a nice slope-intercept form on the TI-84s, but I do have to get the y by itself. Okay, so good. So I'm going to close the parentheses, I assume. Divide by 6. Okay. Yes. Okay. Okay. So we graphed one of them. Now we'll come down and graph the other one, and I get y equals negative. I'll go ahead and put the fraction template in, 1/2 x minus 5. What's that? Did you find it?
No, I just don't have the version that I need for this.
Well, yeah, you can. Just go alpha F1. Mm-hmm. Okay. Yeah. Yeah. Okay. Now, if I hit graph, okay, so those look parallel. How could I tell for sure? Because maybe the slopes are just slightly different. right? I mean, it looks like they're parallel. How can I tell for sure though? Okay, there is a way. I'll show you how. So you could verify this using the graphing calculator. If I go back to the calculate menu, second calc, none of these look like slope, but number 6 means slope. That's our calculus way of saying slope, dy dx. What that really means is, think of it like delta y over delta x, change in y over change in x, right? So if I want to find the slope of those lines, I can just go down and I can type 6. And then if I want the slope of the first line, well, it's on y1, so I just hit enter, and look what it tells me. Dy dx equals negative 0.5. That's the slope of the blue line. If they're parallel, what does the slope of the red line need to be? Negative 1/2. So I just have to do the same thing again. I'm going to go second calc 6. And how do I get to the red line from the blue line? Down arrow or up arrow, doesn't matter. I'm just going to toggle through the different graphs that I've created. There's y2, and I hit enter, and what do you know? The slope is negative 0.5. So I just showed that those two lines are parallel because they have the same slopes. They don't just look parallel, they are parallel, okay? What about on, take a picture of that. Okay, how about on Desmos? Yeah, how do you, there's a way, I'll show you, there's a way to do it. 3x, I can't see that, what is it? 3x plus 6y equals negative 12, and y equals negative 1/2 x minus 5. Ooh, those are the same color, that's no good. There we go. Okay, so how could I tell? Well, I want you to notice something. Like, if I'm going to change the green line for a second, I'm going to change it to one where there is an obvious intersection. What does Desmos do if I click on either one of those lines? What does Desmos do to tell me that there is an intersection? Yeah, there's a light gray point there, which invites me to click on that point and find the intersection, right? The coordinates. Anytime there's anything interesting happening on a graph, Desmos will give you an option to click on that. Notice it has there's the y-intercept of the green line, there's the x-intercept, and there's the intersection, right? Okay, so if these lines intersect, if I click on one of these, like the green line, and I zoom out, what should I see? Yeah, eventually I should see a gray dot appear when I zoom out far enough to see an intersection, but I can go forever and ever and ever and ever and ever and ever, and I never see a gray dot. So they never intersect, do they? Right? Just to show you here, I'll prove it to you that that's really what happened. Let me change this negative 1/2 x. What if I change that? I've never done this before. This is brand new stuff. So what if I make that negative 0.50001? Okay, those look pretty parallel, don't they? Right? But they're not going to be. Oh, this is a good idea. I never thought of this. So if I zoom out here, eventually,
Maybe.
did anybody find it? There it is, right there. Negative 300,000, positive 149,998. I did get an intersection, right? I've never done that before, so I've never actually verified that works, but it does. Okay. Though they are. Okay. Okay, makes sense? Okay. All right, so I'm going to change this one slightly, just on Desmos. I'm going to make this a 2. Okay, what happened? Oh yeah, it's crazy. Look at that. Okay, what happened there? Okay, they're the same line, aren't they? How do I know? Look, if I turn the green one off, the red one is right there. Okay, how would you verify that? Okay, you could verify that. That's a good question because I don't know. I mean, you can see there's how you verify it. There are multiple. If they're lines, they either are going to have one solution or no solutions or more than one solution, right? So if it has more than one solution, Desmos can't draw an infinite number of solutions, but what is it doing? It's telling you that those have to be the same line because they're intersecting more than once. The only way two lines can intersect more than once is if they are the same line. It's a good question. Does that satisfy you? Okay. All right. All right. So to end things up today, we're just going to do a quick review of just the first of two different ways of solving linear equations. We have two methods, right? Substitution. What's the other one? Well, no. Something Asian. Elimination, right? Okay, so there are these two ways to solve algebraically now. So now we're gonna abandon all the graphing technology here. We have to do this using algebra. One way is using substitution. So how does that work? Substitution means I'm going to pick one of the equations and isolate a variable in one of the equations and then substitute that into the other equation. Okay? So let's try this. Now, this, by the way, substitution is really only a good technique to use if it's easy to isolate a variable. Well, in this case, it's already done for us twice. Y is already isolated in both equations. So we'll just pick one of those to use as our substitution equation. I'm going to use the bottom one arbitrarily. When you make a substitution, if you have a variable isolated, always put a box around your substitution equation because you're going to come back to it, as you'll see. So I solve for y in the bottom equation. I'm going to substitute that value of y into the top equation. So the top equation becomes then what is equal to negative 7x minus 1? Y is, but y is being replaced by x minus 9. There you go. So solve that for me. What do you get? Solve that in your head. What do you get? One. Yeah, if I push the x's to this side, I get 8x. If I add 9 over here, I get 8. So x equals 1. Am I done? No, it's a system. I need values of both the variables. So where do I go to find y? Into the boxed equation. How about that, right? So I'm going to plug that right into the boxed equation. In this case, I could have used either one, but in most cases, if it's not already isolated, if y isn't isolated in both equations, which it's usually not, then I'm going to go back to the equation where I already did the work of isolating a variable, right, and plug into that one. So that's the boxed equation. If I plug 1 in there, I get y equals 1 minus 9, which is negative 8. And so I get for my solution then the ordered pair 1, negative 8. Okay. How could I check to see if I get it right on a test? Substitute into both equations and verify that it works. Okay, let's try one more of these. How about this guy? Thumbs up or down? Is substitution an okay way to solve this system? Okay, I'm telling you, it's thumbs up. It's thumbs up. But what's the variable there's clearly one variable that I should isolate here. Which one is it? Well, which variable should I isolate, get by itself? Y in the second equation. How come? Because it's got a coefficient of 1. When we use substitution, we're only going to use substitution if it's easy to use substitution, which means we only use substitution when there is an x or a y, or maybe if we've got more than x's and y's, if we have a variable in one of the equations with a coefficient of 1 or negative 1. So it's really easy to isolate. In this case, it's very easy to isolate this y. All I have to do is subtract 7x to the other side, right? So I get y equals either negative 7x plus 22, or I could even just say 22 minus 7x if I want to, and I'm going to put a box around it. What do I do with that y? Plug it back in the other equation. So it's going to go there, right? So I'm going to get 6x minus 5 times y, which is 22 minus 7x. And there's only one kind of variable there, so I can solve that equation. That's no big deal, right? I can just, what do I distribute the negative 5? So 6x minus 110 plus 35x equals negative 28. If I combine like terms, 41x. If I add the 110 to that side, I get 82. What's x equal to? 2. So I get x equals 2. Am I done? Where do I go? To where? The boxed equation. There you go, right? Look, it's already served up to me. It's already solved for y. So that's going to give me y equals 22 minus 7 times 2. 22 minus 14 is 8, right? So I got my ordered pair. X equals 2, y equals 8. Okay, good. All right, thumbs up or down. How about that one using substitution? Big old thumbs down. There's no variable there that has a coefficient of 1 or negative 1. So if I isolate any one of those variables, I'm going to get fractions. And I don't want to be substituting an expression with fractions in it. So we move on and we don't use substitution. We move on to elimination, which is what we're going to talk about tomorrow. Okay? Okay. There's an assignment up, or there will be momentarily.
Just get